Okay, so autonomous system, autonomous means that the dynamics only depends implicitly on time. There's no kind of external forcing or there's no time built into the governing equations. And we will typically consider them in the form of x dot is equal to f of x. And we're really only going to study, for the most part, we're going to, in the first 6 weeks, we're only going to consider discrete systems. Discrete in the sense that they are discrete masses and not continuous vibrating systems, not discrete in the sense of maps. We will study discrete maps, which is different than a vector field, but we're going to look at discrete dynamical system, I guess we'll say. Discrete in terms of space, but continuous in time. Okay, so we have some differential equation, x dot is equal to f of x, where here x is a function of time only, doesn't depend on space, and it lives in the space Rn, meaning that it is a vector of real numbers, basically. And there are n, in this sense, you can think there are n state space variables. Has everyone here done and seen state space? Has anyone not seen state space? Okay. Yeah, so we're working in state space coordinates here, or what we would call phase space. Okay, so this function f is a mapping from the set U, maps the set U to Rn, and U is some subset, or it could be Rn. Some subset of Rn, or it could be Rn. All right. And U tends to be our initial conditions, is what we're thinking here. U will be our initial conditions. And again, it can be a subset of Rn, so in some systems you may not have the same number of initial conditions as you do have the number of phase variables. In vibrating structures, they're typically equal. But this is general. Okay, so for the function f is going to be smooth on the subset U, which again is a subset of Rn. And then we can say that the vector field f here generates a flow, which will say phi sub t, which maps U to Rn. Where this phi sub t of x is equal to some function phi x comma t. So we'll see a picture in a moment when I can get the screen low enough to kind of talk about what a flow is in general. But it's a smooth function, and it's defined for all x in U and for t in some interval, which we'll say is I equal to a comma b, and this is again a subset of the real numbers. Not Rn, just R. Okay. So here the flow phi is going to satisfy our original differential equation in the sense that we can say d phi x comma t dt evaluated t equals tau. This is then equal to f of phi x comma tau and this is valid for all x in U and tau in that interval I. All right. Okay, so we're getting close to these diagrams. So we're often going to be given some type of initial condition, which is x at some t0. And we'll say that's equal to x0, which is again a subset, which lives in that space U. And we're trying to find a solution phi of x0 comma t such that that flow phi of x0 t0 is equal to x0. In this case, we get the following map. We get phi x0. Instead of putting t0 there, I'm just going to put a little dot there because it ends up being arbitrary. Phi then is a mapping from that interval I to Rn. You can think of it like that. And here we've left out t0 because it ends up being an arbitrary time. We'll call this phi of x0, this map here, we can call this a solution curve, an orbit, or a trajectory, and all three of those terms are the same thing in the context, at least of this course. If we take a look at this diagram here, what we're seeing in that circle, that black circle, is U, so that you can think of as our space of initial conditions where we're starting. Our solution curve, or phi of x0 comma t, that starts at x0, which lives in the space U, and then this system is then evolving along this solution curve phi into Rn. And so here we can say that that U is the domain of the solution curve, and that solution may end up leaving that U. Okay. So what we're interested in is really more families of these solution curves and how they evolve and what their global behavior is. And we can say that the global behavior of the flow phi sub t mapping U to Rn for x in U. Okay, so what we have here is in the diagram on the right, in that bottom circle, you can think about this U being our initial conditions, our starting points down here. And this flow phi is what maps all of these starting points to where the dynamical system ends up and what the values of those x's are at some later time t. And so what we're interested in is understanding these solution curves or these trajectories of how the system evolves over time. Okay.
Sorry.
Yeah.
The thing that you said multiple solutions exist, I see in the map, we can, pass different kind of, trajectories from the x off, right? So it exists infinite number of solutions to one initial condition.
It's a great question. So it depends is the answer. It depends on the system. And so just the question was, since we talked about multiple solutions existing, does one of these points in U, does that map to an infinite number of solutions at time t? I don't know about infinite, but it could map to multiple. It might be infinite, depends on the system. The thing is, it depends on the system, really. And we will see cases where we can have 3 different solutions at the same time, and one solution will be unstable and 2 will be stable. And there are cases you could create where you can have more than 3. Infinite, maybe. I don't know.
Are we talking for the same system, for the same parameters of the system?
No, for different systems.
Oh.
Yeah. So we will see, when we do like a Duffing oscillator, we'll see that it can have 3 solutions at a time. And then there's the possibility for maybe a 2-degree freedom to have more than 3 at a time. And then it grows. For a continuous system, which, you know, it depends. It depends on the system. You have to approach and study each system independently is the key thing here. But the techniques we can use can be applied to many different systems. But that doesn't mean that what you learn from those techniques will be the same for each system. That was a good question, though. Any other questions? Okay, so I think I just threw out the word vector field here without explaining what that is. Or maybe I did. So anyway, when we're thinking about a vector field, what we're talking about are systems that are continuous in time. So like a simple harmonic oscillator is a system that is continuous in time. And what we're going to talk about is also discrete systems called maps. And there's an overlap in terminology throughout some of these things. So we talk about how phi here, you know, is a map defining a solution curve. There are some overlap in terminology. But when we talk about a dynamical system that's a map, we're usually thinking of something that's discrete in time. And so what that means is that we'll have a system X, which is mapped to some function g of x with a parameter u, and that is equivalent to writing it out in an iterative scheme. So x at n plus 1 is equal to that function g evaluated xn with that parameter u, mu. We will see this, I think, in week 6. Somewhere around there, we'll come back to the idea of what a discrete map is and how we can study bifurcations of those systems. What else should we add here? So where x here lives in U and is a subset of Rn, and U is an open set. Okay. What we're going to focus on is autonomous vector fields, which are systems that you are familiar with. Typically, things like the pendulum is a vector field. Oscillators are vector fields. And they're going to have the form x dot equal to f of x, where we'll say here x lives in the space D, which is a subset of Rn, and x here is equal to the vector x1 up to xn, and we'll just throw in a transpose there, and we'll call this equation 1. Okay, so there are several different types of classes of solution that we will generally be interested in or could be interested in. The first is just equilibrium points. The second is periodic, quasi-periodic, or chaotic orbits. And then the third, which we won't really deal with ever in this class, are known as solutions on integrable manifolds. Okay, we have 2 minutes, so we're just going to start our discussion on phase space orbits, and we'll then continue that on Thursday, starting with this part right here. Okay, so we're going to suppose that 1 has a solution x is equal to phi of t. then we can say that x is equal to phi of t minus t0. Let me write that a little bit smaller. Where t sub 0 is some arbitrary constant. And what this tells us is that when we have the solution phi for an autonomous system, it's not going to be dependent on time. That flow phi is not dependent on time, meaning that we can arbitrarily shift along in time and still have a solution to that equation. So we're not necessarily talking about, specifically a displacement or velocity at a particular point in time. We're talking about the overall solution to that system and how it will not change with respect to time. Again, this is for autonomous systems. That means undamped, well, not undamped, but in this case, we're considering undamped. You can see that there's not a dependence on that x dot up there. Well, no, it could be damped, actually. I'm wrong. It could be damped, but it's not forced. That's my point, where I want to.
T doesn't exist
Yeah,
in the equation.
right, exactly. And then here's this proof on the aside, shown right there. And the key thing here is that the solutions of autonomous vector fields are time and translation invariant. That means they remain solutions under time translations. On Thursday, we'll draw some of these vector fields, or draw some of these solution curves in the phase space, and then we'll talk more about this time translation invariance. Okay.